Okay, so in this segment, what I want to talk about is something called currying, which is the idea of functions that return other functions as output. So last week, and in the homework that you're working on now, we talked about functions that take functions as input. And this is kind of the dual thing where we're going to have a function that gives another function back as output. And if you remember from last week, we're working on map for lists, right? So the idea was map is the function that goes through and applies a function, given function f, to every element of a list. And for example, one of the examples we did was the raise by or add to each function, which was one way to write it is if you're giving everyone in L a raise by C dollars, then you map the function that sends each X to X plus C on L. So for example, if you give everyone in the list 1, 2, 3 a raise by 1, then you get 2, 3, 4, right? And the reason that you get that is that what it's doing is it's going through and it's applying the function that adds 1 to 1, and then applying that to 2, and then applying that to 3, and when you do that, you get 2, 3, 4. Okay, so one way to write that was using what we talked about last week, an anonymous function, which is the function that sends x to x plus c. Another way to write that we talked about last week was you could define the add c function in here to be x plus c in that. And if you do that, then you could then map add c on L there. Fun add c. Okay. And then we would still get the same thing. Okay, and so what this is doing is it's defining the add c function locally to raise by. But maybe the function that you're mapping gets used in many places in your program at once, since you don't want to define it inside the scope of the C, right? The trick here was that this is inside the scope of the C. Maybe you want to try to like move the function. Okay, in this case, it's not that complicated, but if it was a more complicated thing, you would want to try to move it out there so that, you know, down here in some other function, you can also map add C on some other list, etc., without redefining the function. Okay, so imagine that add C was more complicated and we didn't want to do that. Well, we can't do that like this because the C doesn't exist here, right? There is no C in scope, so we can't define add C out here. But what we can do is use this idea of currying, or functions that return other functions, as output to do it. So the idea of a curried function is that if you think about just like adding two numbers, then the type of add as a function is that it takes a pair of ints and gives you back an int. Okay, so what we could do instead is define what's called a curried add function, which takes x, which is an int, and gives you back a function from ints to ints. Okay, well, what function does it give you? It gives you the function that takes in a y and gives you back x plus y as the overall output. Okay, so what we're doing is we're changing a function that takes a pair of ints and gives you back an int into a function that takes an int and gives you back a function from ints to ints. So we're returning a function as an output of our function. That is, when you give curried add an input, it gives you back a function. What function is it? It's the function that gets in a y and then does something with it. Okay, so let's run it a little bit as some examples. If I do add of 3, 4, right, that's calling the plus function on 3 and 4, I get 6. If I do curried add on 3, that gives me back a function. Well, what can I do with a function? I can apply it to an input, and if I give curried add of 3 the input 4, then I get back 7 because it's now getting a y and doing the actual addition. So what's happening here is that curried add is outputting, like if we tried to explain what's happening when we step it, curried add applied to 3, how do we evaluate that? Well, we do the same thing we've always done. We plug in 3 for x, so we get the 3 plus y function there. And then if I was to do curried add of 3, which is a function itself applied to 4, then I get the function that sends y to 3 plus y applied to 4, which then, well, how do we run that? We substitute, and so we get 4 plugged in for y, which then steps to 7. So that's how that's working there. Okay, so there's a little bit of syntactic sugar that you should know about, which is that when I wrote down here curried add of 3 itself applied to 4, you can write that without the parentheses. So if you say curried add space 3 space 4, that's applying the curried add function to its input 3, and then applying the resulting function to the input 4, just like what we were doing before. That means the same thing as it meant before. And, okay, so thus far, right, it's just another way of writing the same kind of thing we could have written with add, right? So like add of 3, 4, and curried add space 3 space 4 without the parentheses do the same thing. So the reason that currying is useful is that if I want my add C function here, well, I can give it C as an input and have it return an int to int, which is the function that sends x to x plus c. Okay, so like my add C function is really like the same as curried add, right? I've just given a different name to the function and to the input. And then down here, what I can do is I can partially apply, this is called a partial application. I can partially apply add C, that is, the thing that I can do with a curried function that I can't do with a regular function is I can give it one of its 2 inputs, but not the other one. So add C applied to C, right, is saying there's a function named add C. Okay, like there was no reason to like define it again. I could have just called curried add. Okay, curried add of C is saying give me the C that is input to raise by, give that to curried add, that produces the function that takes X and adds C to it, and then do that on L. And so now the same thing will happen as before, which is you get raised by of 1, 2, 3, gives me back 4, of 4 is, okay, adding 4 to everything in the list, great. But now what I can do is that I'm referring, just like in the version where we're defining the input to map in the let, I'm giving it a name, so I can give it a name so that, but now I can give it a name outside, right? So out here I can define curried add. So if curried add were more complicated, right? So if this were like went on for a while, was some big long piece of code, I could give it a name out here. And so I could use it in multiple different places. So here, if I want to do a curried add with something else somewhere out here, then that's okay because it's defined outside of raise by. But now I've got the ability to give it one of its two inputs and not the other. Okay, so the overall idea of currying is that you have functions that return other functions as output. And kind of the idea is that you can give a function some of its inputs, but not all of them, getting back a function of the remaining inputs. Okay, so that's the main idea. There's a little bit of notation that we should talk about, which is there's syntactic sugar, right? So this just means an abbreviation for the exact same thing, where if you don't want to write curry at add of X is the anonymous function in Y that gives you back X plus Y, then you can write multiple groups of inputs separated by spaces instead of commas, and that'll give you a curried function. So if I define things like this, it means exactly the same thing as curried add of X is the function that takes Y to X plus Y, but I can define it like that. Okay, so everything that we said before still holds. It's just a different notation. Okay, and then if you kind of use the same notation for applying it, if I've got curried add of 5 and 6, right, I just write them with spaces. So, okay. So the last thing to comment on is that we can curry a lot of the functions that we've done before. Okay, so for example, for map, it's actually more customary to define it like this. Map of f is the function that takes f and returns a function that takes a list to another list. And one of the reasons that it's customary to do map like that is that then you can think of it as what map is doing is it's taking an A to B function and giving you back an A list to B list function, right? That's especially apparent if we don't use the syntactic sugar, and instead we say map of A to B is the thing that takes an A to B to an A to B list. is map of f takes an f which goes from A to B and gives you back an A list to B list function. So a way to think about it is that what map is really doing is it lifts a function f that acts on elements to act on lists instead. All right. And one of the things that you can do once you've queried it, something like map, is that if you have looked at the written part of the homework handout already, then there's this idea of function composition, which is the thing that takes two functions, an A to B and a B to C, and composes them into an A to C function. So this is actually function composition is built in to XML. It's written with a lowercase o. And the idea of function composition is that it takes a B to C function and A to B function, gives you back an A to C function. And so one of the reasons that people like currying is that you can define other functions by composing together functions. So for example, if I apply curried add to 4, that gives me the function that adds 4. If I apply curried add to 6, that gives me the function that adds 6. If I apply map to curried add of 4, that gives me the function that adds 4 to every element of a list. If I apply map to curried add of 6, that gives me the function that applies curried add of 6, add 6 to every element of a list. If I then compose those two functions together, I get a function from int list to int list. And what does it do? It does one after the other. So if I apply that whole thing to 1, 2, 3, 4, 5, well, adding 4 and then adding 6 is adding 10 to every element of the list. So that's the same as mapping curried add of 10 on the list. But they're the same, not just at the level of if I apply them to a specific list, like 1, 2, 3, 4, 5, then they're the same. They're in fact the same function overall. And it's slicker to say that if we use currying, because now I can talk about the fact that the function that you get by composing together these two things is the same as, in the sense of the same on all inputs, the function that you get by mapping curried out of 10. So a slicker way to say what was happening in your written homework is that map G compose map F is the same as map of G compose F. And that's true, like, without even giving the two sides an input list, just as functions, those two are the same function. Because, well, what does it mean to be the same function? It means that you have the same value or the same behavior on all inputs. Okay, so to some extent, this is just kind of a convention, but it's going to be the case that some of the stuff we're going to talk about going forward is dependent on like these curried ways of thinking about functions. So I wanted to talk about that first to get off the ground. And if you're wondering, like, why is it called currying? This is named after a mathematician named Haskell Curry, who was one of the first people to consider this idea. Okay, so now we've seen a little bit about currying, and in the next segment, we'll move on and use that for some stuff.